Today we will find out the moment of inertia of hollow and solid cylinder. So suppose this is our hollow cylinder and we have to find out the moment of inertia. So along say this axis, as we know that this hollow cylinder is made up of many rings like 1, 2, 3, 4 and up to so on. So if I take a ring of mass dm, so we know that the moment of inertia of a ring along the axis perpendicular to the ring is I is equals to dmr square. So if I integrate the moment of inertia for all the rings in the hollow cylinder, then it will become, suppose this is I dash, then I will become summation of dmr square, and r is constant, so I can take it outside the summation. The summation of dm r square m, and this is a r square. It's the moment of inertia of hollow cylinder. Now suppose if this cylinder is a solid cylinder, then I can assume that this cylinder is made up of many discs, 1, 2, 3, 4, 5, 6. So for the disc, moment of inertia is I dash dmr square divided by 2. So for this, moment of inertia for the solid cylinder will be mr square by 2. This is for solid cylinder and this is for hollow cylinder. Now this is the moment of inertia along the axis which is passing through the center of the cylinder, and it is along the length of the cylinder. Now if you want to find out the moment of inertia along an axis which is perpendicular to the length of the cylinder and passing through the center of mass of the cylinder, so how can we find out the moment of inertia along this axis? Now this is our solid cylinder and this is the axis which is passing perpendicularly to the length of the cylinder and center of mass of the cylinder. So let's say this is a disc in this cylinder and its width is dx and it is of distance x from the center of mass of the cylinder. Now let us consider a solid cylinder of mass m and radius r. And having density as rho. Let's say this cylinder have density rho. Now, rho is mass per unit volume of the cylinder. So mass of the cylinder is m and volume of the cylinder is pi r square h. Let's say this is an axis which is passing through the center of the disc and along the diameter of the disc. So if we want to find out the moment of inertia along this axis for this disc, then I can write it as, let's say this axis is AB and this axis is PQ. And I am denoting dash as the moment of inertia for the disc. So I dash PQ. Is equals to mass of this disc. Now mass is rho into area into width. Rho into volume is mass of this disc. Volume of this disc. We will take volume of this disc, no, not for the cylinder. If we take the volume for the cylinder, then it will be the mass for this cylinder. So I am taking the volume for this disc, that is pi r square and dx. Pi r square is the area of this disc and dx is the width of this disc. Now I dash PQ is equals to rho pi r square dx. The moment of inertia for the disc is mr square along this axis is mr square divided by 4. So m r square into r square divided by 4. This is the moment of inertia along PQ of this disc. Now we will apply parallel axis theorem. See, this axis is passing through the center of mass of this disc, and if we want to find out the moment of inertia along AB for this disc, then the theorem says that I dash AB is equals to moment of inertia along an axis which is passing through the center of mass of this disc PQ plus product of mass, that is rho pi r square dx. Mass, product of mass multiplied by square of perpendicular distance between them, that is x square. This is our parallel axis theorem. Now from here, I dash PQ is rho pi r square dx. R square will become r raised to the power 4 divided by 4 plus rho pi r square dx. I can write it as x square dx. X square dx. Now this will be our I dash AB. Now I dash AB is equals to, now we'll take rho pi r square from both the terms. Rho pi r square. The remaining term will be r square divided by 4 dx plus x square dx. Now see, this I dash AB is the moment of inertia along AB for this disk, and we have to find out the moment of inertia for this cylinder. So if we integrate I dash AB for this cylinder, then we will get the moment of inertia of this cylinder. So integrating both sides, from this side we will get the moment of inertia for this cylinder, and see, from this side if we integrate dx, this term, if we integrate this dx from this to this side, then we will get the complete cylinder, solid cylinder. And if this point is 0 and this point is x, then from this point to this point the length will be minus L by 2. The length will be L by 2, and this point is minus L by 2, and this point is L by 2, so that the length of the cylinder will become L. So IAB is equals to rho pi r square r raised to the power r square divided by 4 dx plus integration of r square divided by 4 plus x square dx. This term is constant, so I took it out outside the integration directly. Now IAB is equals to rho pi r square divided by 4 now we'll integrate this term. This is a constant term, and the integration is with respect to dx, then this term will become r square divided by 4 into x plus integration of x square is x raised to the power 3 divided by 3. So now we will put the limit. The lower limit for x is minus L by 2 and the upper limit is plus L by 2. So I am putting here the lower limit as minus L by 2 and upper limit as minus L by 2 plus L by 2. Rho pi r square divided by 4 L by 2 minus L by 2, so it will become plus L by 2 plus 1 by 3 is constant, so I will take it outside the bracket. X cube L cube divided by 2 to the 4 to the 8 minus plus L cube divided by 8, and this bracket is closed. Rho pi r square divided by 4 L by 2 plus L by 2 is L plus 1 by 3 L cube by 8 plus L cube by 8 is L cube by 4. Now we'll put the value of rho, that is m divided by pi r square L. Pi r square divided by 4 into L plus 1 by 12 L cube. From here pi r square to pi r square cancels out. Now if I open this bracket, it will become m divided by L r square by 4 into L plus m by L m by 12L to L cube. From here L will cancel out from L, then 1 by 4 mr square will get plus, from here L cancels out with the power of L raised to the power 3, and it will become 2 m by 12 L square. This is the moment of inertia for the solid cylinder along the axis AB, which is passing through the center of mass of the cylinder. Now what if we want to calculate the moment of inertia along the axis which is passing through the end of the cylinder? Suppose an axis is passing through this end of the cylinder. So how we'll find out the moment of inertia along this axis? Now we know that the moment of inertia along this axis is 1 by 4 mr square plus 1 by 12 ml square. So from the parallel axis theorem, we can easily find out the moment of inertia along this axis. That this is PQ axis. So from the parallel axis theorem, IPQ is equals to IAB plus this distance will be L by 2 m L square by 4. Moment of inertia along an axis is equals to the sum of moment of inertia along an axis which is passing through the center of mass of the cylinder plus the product of mass and perpendicular square of perpendicular distance between both the axes. Now IPQ is equals to 1 by 4 mr square plus m by 12 l square plus ml square divided by 4. 1 by 4 mr square IPQ so from here if I multiply 3 on the numerator and denominator, then it will become 12 and here we'll get 3. So 3 plus 1 is 4. 4 ml square divided by 12. IPQ is equals to 1 by 4 mr square plus ml square divided by 3. So this will be the moment of inertia along PQ.